Welcome to our second module, which is dedicated to quantum search algorithms. Today, we're going to be discussing the Deutsch-Jozsa algorithm. On a technicality, it is not quite a search algorithm, but it will introduce a certain number of concepts that we will be needing to present the Grover search algorithm and quantum amplification. So here we assume that we're given a function f, which is a Boolean function. It is from 0, 1 to the n to 0, 1, and it's either constant or balanced. Constant means that f of 0 will be equal, f of x will be equal to f of 0 for every x. Balanced means that there is going to be an equal number of f of x equals 0 and f of y equals 1. And then the problem here is to decide whether f is constant or balanced. Now, this problem itself is not so hard to solve if you can query f, a circuit that evaluates f for enough inputs, okay? If I tell you here is a box that will give you evaluations of f, then I need to decide whether or not f is constant or balanced. What I need to do is to query this function for half of the inputs plus one element, and then I will be able to decide for sure. Here, in the quantum setting, we'll show that we can answer this question with only a quantum circuit that evaluates f only once. So let's see how this does. Now, we need first to introduce the notion of uniform superposition. This is something that we have not been dealing with so far in the course. So uniform superposition, assume you have a set of indices between 0 and 2 to the n minus 1. The state psi, which is the sum of basis vectors corresponding to the indices in the set divided by square root of the cardinality of S, is what we call the uniform superposition of the elements of S, right? And the probability of measuring a given S is for every a given X is for every X, it is 1 over square root S square, which is 1 over S, which is a uniform probability. Now, we're going to figure out a way to create uniform superpositions over all possible outcomes. And this is going to be done with the Hadamard gate. So remember, the Hadamard gate is one of those elementary gates from our gate set, and it has this shape. And we have in particular that h of 0 is given by 1 over square root 2, 0 plus 1 over square root 2, 1. And this is exactly a uniform superposition of all the elements, well, 0, 1 in this case, okay? So this is the simplest uniform superposition that we can make. Now, slightly more complicated. If I tensor Hadamard and I apply it with 0 tensored with itself, so what do I get? I get h applied to 0 tensored with h applied to 0, and that is 1 over square root 2 times 0 plus 1 over square root 2 times 1 tensored with the same thing, 1 over square root 2 0 plus 1 over square root 2 1. And I expand this into 1 over 2 0 0 plus 0 1 plus 1 0 plus 1 1, and this is the uniform superposition for S equals 0 1 2 3. Okay, so exactly the uniform superposition over all possible outcomes of a measurement on 2 qubits. Okay, now this result is going to naturally generalize by doing the same trick. So if we have h tensored n times, and we apply this to 0 tensored n times, then each of these terms here is 1 over square root 2, 0 plus 1, okay, tensored with 1 over square root 2, 0 plus 1, etc., until 1 over square root 2, 0 plus 1, okay? And now if you expand this, what you get is 1 over square root 2 to the n. You can kick all those square root 2's out of the sum, out of the tensor product. And then what you get is you have 0, 0, 0, 0, plus 0, 1, plus, you can verify the calculation until you have all the ones here, okay? So you have here the uniform superposition over all the possible measurements on n qubits. Now the Hadamard gate has a slightly more intricate behavior when it comes to acting on a non-zero state. This is something that you have to prove in a homework assignment, but here we're just giving the formula without a proof. So if you apply h tensored n times to an x that is not necessarily 0, you'll get a state with the same normalization factor as before, but here the phases are going to be -1 to the x dot y, where x dot y, since x and y can be viewed as n bit strings of length n, we're talking about a dot product of those vectors in F2. So x0, y0 XOR, x1 and y1 XOR, etc., until you have x minus 1, y minus 1, okay? So this is how in general the Hadamard gate applies. Okay, so now we will start with a smaller version of the Deutsch-Jozsa algorithm, which is just the Deutsch algorithm. It's Deutsch-Jozsa, but on 2 qubits. I mean, so f is a function from 0, 1 to 0, 1. And in this case, we're asking still the same question: is f balanced or constant? Which can be rephrased as, is f of 0 equal to f of 1, or is f of 0 different than f of 1? Okay, and again, if I was to ask you this question and then give you a box that evaluates f, then classically you would be required to query this box twice in order to answer the question: is f of 0 different or equal to f of 1? Here, in the quantum setting, our circuit is only going to make use of a circuit that evaluates f once to answer this question, which is very impressive. So the goal here is to decide if f of 0 equals f of 1, f of 0 is different than f of 1. Okay, so here is the main components of the evaluation of f. Okay, so it is a circuit that takes A and returns A, and takes B and returns B XOR f of A. So we've seen generic techniques to produce such a circuit from the description of the function f. And we assume when we say evaluations of f, we mean the number of times that this item shows up in the diagram of the quantum circuit. Okay. So this is the quantum circuit in question. As you see, this component that evaluates f is only showing up once. Now we will have 2 qubits coming in, going through a Hadamard gate tensor twice, and then at the output only 1 Hadamard gate, and we're going to perform the measurement here. Okay, and we will show that if the measurement is 0, it tells us for sure that f of 0 is equal to f of 1. So in this case, what it means is f is constant. Otherwise, f will have to be balanced. Now, here we have, at the very beginning, we start with a 1 here and a 0 here. Okay, so we have a case of h tensored twice for an input that is not 0 tensored with itself. So here what we have is 1 over 2, 0 plus 1, tensored with 0 minus 1, okay? And that, in turn, is 1/2 0 tensored with 0 minus 1. So I'm just expanding here the product, plus, I guess I could have the bracket here, so 0 plus 1 tensored 0 minus 1, and I close the bracket. Now let's see what happens after I get the action of u sub f here. So we have that u sub f tensored with our previous state here is going to be given by the action on each term. So we had a sum of 2 terms, and now we're wondering how this action will look like once we simplify for the different values of f. So if f of 0 is equal to 0, then what do we have? Then we have that f of 0 minus f of 0 XOR 1 is equal to precisely 0 minus 1. On the other hand, if f of 0 equals 1, then f of 0, the state f of 0 minus the state f of 0 XOR 1 is going to be equal to 1 minus 0. So altogether, we always have minus 1 to the f of 0 times 0 minus 1. And the same holds true for the other term. So this other term is going to be, so we're going to have that f of 1 minus f of 1 XOR 1 should be equal to minus 1 to the f of 1 times 0 minus 1. So there is a good way here to simplify the state that we get. Indeed, so remember here, this is the state that we're looking for here, where we get, if we factor by 0 minus 1 and minus 1 to the f of 0, what we get is minus 1 to the f of 0 times 1/2 of 0 plus minus 1 to the f of 0 XOR f of 1 tensored with 0 minus 1. Now this is made possible because we've factored by 0 minus 1 on both terms, but also we've noticed that if you expand this minus 1 to the f of 0, it will cancel out when you have, I will write down here, if you have minus 1 to the f of 0 XOR f of 0 XOR f of 1, this is going to fall back to minus 1 to the f of 1. So that allows us to factor with this global phase, and this can be ignored. Remember, a global phase will not contribute to the final measurement. So we'll say that this is equivalent up to global phase to the state 1/2 0 plus minus 1 to the f of 0 XOR f of 1 times 1 answered with 0 minus 1. Okay? Now let's see what will happen once we apply the second Hadamard transform. So if I apply the Hadamard transform, so because we get a product state, what happens on the second qubit can be totally ignored. I have a product state, the second qubit is now living its life independently from the first one. So now we focus on what happens on just that one qubit when we apply the Hadamard transform. The state of that qubit is going to be what we see above. Now, what we have is two cases. We have either f of 0, if f of 0 equals f of 1, then what we have, and I apologize for the typo here, so this is times 1. So if f of 0 equals f of 1, then what we have is f of 0 XOR f of 1 is going to be 0, regardless of the value. If it's a 0, if it's a 1, the XOR will tell you the same. Now, if f of 0 is different than f of 1, and again here, regardless of what those respective values are, we have that f of 0 XOR f of 1 is going to be 1. So in this case, I'm looking at the state 1 over square root 2, 0 plus 1. While in this case, I'm looking at 1 over square root 2, 0 minus 1. And when I apply the Hadamard gate on this, I will recover 0. And when I apply the Hadamard gate on this, I recover 1. Okay? So in the end, if I measure 0, I know that I was in the case f of 0 equals f of 1. On the other hand, if I measure 1, then I know that I was in the case of f balanced, which means in this case, f of 0 is different than f of 1. So now we've shown how applying the circuit that evaluates f only once, we get to a state that once it's measured tells you exactly if f is balanced or constant. We're going to do this now in more generality for an f that has an n-bit input. So we have the circuit for f, of course, since f is on n qubit, since f is on n bits, then we have a circuit here that generalizes the circuit for the Deutsch algorithm, okay? So here we have our n qubit state. Now, what happens? We will do the exact same thing as before. We will push a 0, this time, of course, it's on n qubits, and a 1 on the last qubit. And then everybody will first get a Hadamard transform, then the circuit implementing f will be applied, and then Hadamard here will have a product state at the end where this qubit will be ignored and this qubit will receive a Hadamard transform again, yielding in the end a state that once we measure it, we will know for sure if f is balanced or not. As we did previously, now we're going to apply the Hadamard transform n plus 1 times to our input state here. So this is going to factor as Hadamard transform applied n times to 0 answered n times, the whole thing answered with Hadamard applied to 1. Now, so this is going to be the uniform superposition over all possible values between 0 and 2 to the n minus 1, and this is just going to be 1 over square root 2, 0 minus 1. So I can rewrite this whole thing as 1. If I factor by the normalization factors, I get 1 over square root 2 to the n plus 1 times sum for x strictly less than 2 to the n of x tensor with 0 minus 1. Now, what happens once we apply UF to the states? So applying UF to the states can be done so by linearity. It applies to every individual term in the sum. So every individual term in the sum will give you something of the form x tensored with, the sum of x tensored with 0 XOR f of x and minus x tensored with 1 XOR with f of x, because it depends on the value of the qubits that is coming here, okay? So we have here a superposition. Now let's see what happens once we expand this sum. We'll play the same trick as with n equals 1, but here, of course, we'll have a slightly more intricate expression. The same way that we did before, if f of x equals 0, then what we have is f of x, the state, so f of x minus 1 XOR f of x is going to be simply 0 minus 1, which turns out to be minus 1 to the f of x times 0 minus 1. And now inspecting the other case, if f of x equals 1, then the same thing, f of x minus 1 XOR with f of x is going to be this time 1 minus 0, which will also be minus 1 to the f of x times 0 minus 1. So this will allow us to factor the sum by 0 minus 1, which is going to be the state of the last qubit, which, as we did before, is going to be ignored. So what we have here is that psi2 can be rewritten as 1 over square root 2 to the n plus 1 times the sum over x strictly less than 2 to the n of minus 1 to the f of x times x tensored with 0 minus 1, the state of our last qubits. Now, what happens, so the last qubit in the state 1 over square root 2, 0 minus 1, we can ignore the same way as before. So now we're focusing on what happens here, okay? So what happens on the first n qubit? We have the Hadamard matrix tensored n times applying to a sum of minus 1 to the f of x times x, okay? So this is going to be, if we expand this product with the known action of Hadamard tensored n time on any n qubit basis states, we have 1 over square root 2 to the n sum over x strictly less than 2 to the n of minus 1 to the f of x times Hadamard applied to x, which is going to be a 1 over square root 2 to the n minus 1, sum over y strictly less than 2 to the m, and minus 1 to the x dot y times the basis state y. Okay, and we can swap the summation to give us 1 over 2 to the n sum over y less than 2 to the n of each term refers, if each coefficient corresponding to a given y is going to be the sum over x less than 2 to the n of minus 1 to the f of x times minus 1 to the x times y, and we close parenthesis. And so now the question is, what is the probability? So when do we measure y equals 0? So the probability of measuring y equals 0 is going to be 1 over 2 to the n sum for x strictly less than 2 to the n of minus 1 to the f of x squared. Okay, and that's because these terms in y are going to cancel, and we are left with the sum of the minus 1s to the f of x. Now, when f is constant, regardless of if f evaluates to 0, f evaluates to 1, this sum is going to be 1. And therefore, the probability here, it's going to be 1. And if f is balanced, the probability, so the sum here is going to be for each minus 1 to the 0, there's going to be a matching minus 1 to the 1 to cancel it. So the whole sum is going to be 0, and for f balanced, the probability of measuring 0 is going to be 0. So we know for sure at this stage that if we measure 0 here at the end of the circuit, we know for sure that f is constant. On the other hand, whatever else we measure, we know f is balanced. So that's the end of our lecture on Deutsch-Jozsa algorithm. Next time, we'll be talking about actual quantum search, and some of those main ingredients, namely U sub f, or the uniform superpositions with tensoring Hadamard gates, are going to come back. So this really justifies inserting Deutsch-Jozsa in this module. Thank you for your attention.